Welcome to the deep dive. Today, we're embarking on an exploration into a really foundational chapter from Timberlake's Chemistry, an introduction to general organic and biological chemistry.
That's right.
Our mission, really, is to pull out the most crucial insights into chemical quantities and reactions and show you how this stuff, which can seem abstract, is actually the fundamental language for understanding, well, health, life sciences, and pretty much the world around you.
Indeed.
Yeah.
We'll try to strip away any, unnecessary
I
jargon
would.
to really reveal the essence of how chemists quantify the microscopic world, describe how matter changes, and even measure the energy involved.
Right.
And what's truly fascinating is how these principles, these basic ideas, they form the bedrock of everything from, say, developing life-saving medications to understanding the complex biochemical pathways inside your own body.
And to really ground this deep dive in something tangible, we're going to start with a real-world scenario. It's actually from the textbook involving someone named Natalie.
Right, Natalie. So, unfortunately, she was recently diagnosed with mild pulmonary emphysema, and it was linked to secondhand cigarette smoke.
Oh, wow.
Yeah. So to understand her condition better, her exercise physiologist, Angela, conducted a pretty comprehensive assessment.
Okay.
This meant hooking Natalie up to an electrocardiogram, an ECG, to monitor her heart's electrical activity and rate.
Like standard stuff, yeah.
And a pulse oximeter measured her pulse and, really critically, the oxygen saturation in her arterial blood.
The O2 sats.
Exactly. And then, of course, a blood pressure cuff to capture her heart's pumping pressure.
So that's quite a bit of data Angela gathered there. What were the key findings? What did those numbers really tell them about Natalie's condition that's, significant for us here?
Well, the big one was her blood oxygen level. It came back at 89%.
89. Okay. And normal is?
Normal pulse oximeter readings are typically 95% to 100%, so 89%. That immediately signals her O2 saturation was significantly low, putting her in a state of hypoxia, basically. Her tissues weren't getting enough oxygen.
Ah, okay.
And this finding, it precisely explained her symptoms, the shortness of breath, that persistent dry cough,
I see.
which led to a diagnosis of interstitial lung disease. So Angela then worked closely with Natalie to improve her respiration, her overall fitness, constantly monitoring her heart rate, blood O2, and blood pressure during exercises.
Natalie's situation, it really just underscores the incredibly fine chemical balance our bodies have to maintain, doesn't it?
It does.
I mean, even seemingly small shifts in metrics like blood oxygen, they aren't just numbers. They're immediate signs of, well, complex underlying chemical issues.
Dysfunction.
Exactly. It just highlights how chemistry, even at this fundamental level, really dictates our well-being.
Absolutely.
Okay, so let's unpack this a bit. Our first kind of critical stop is about how chemists actually deal with things too small to see or hold, atoms and molecules. How on earth do you count something that tiny in practical, usable amounts?
Right. Well, given how impossibly small individual atoms and molecules are, chemists needed a bridge, really, a practical link between that microscopic world and the amounts we can actually measure out in a lab.
Makes sense.
And that's where the mole comes in. It's our fundamental counting unit in chemistry. It precisely connects the number of particles to a measurable mass.
A mole, like the animal.
No, not quite.
Yes.
Spelled the same, but a totally different concept. Think of it like a dozen for eggs, right? A specific number.
Okay, got it. So a chemist's dozen.
Kind of, but
Yeah.
much, much bigger. 1 mole of any substance contains 6.02 by 1023 items.
Wow.
That huge value is known as Avogadro's number.
672 sextillion. It's an immense number. But I guess it has to be because atoms are so incredibly tiny.
Exactly. So 1 mole of carbon atoms contains that many carbon atoms. 1 mole of water molecules contains that many water molecules.
Right.
It allows us to connect the unseen world to the tangible things we can actually weigh and measure.
Which brings up the next question. If we can count them this way, using moles, can we weigh them? And I guess why is weighing them so crucial?
Precisely. And yes, we can, effectively. That brings us straight to the concept of molar mass.
Molar mass. Okay.
Now, a single atom or molecule, far too tiny to weigh individually, as you said. But in the lab, we can measure the mass of Avogadro's number of particles. That is the mass of 1 mole of a substance.
Ah, okay. So the molar mass is the weight, well, the mass in grams, that numerically matches the atomic mass of an element from the periodic table.
Exactly. If carbon has an atomic mass of, say, 12.01 atomic mass units, then 1 mole of carbon atoms has a mass of 12.01 grams. Simple as that.
Okay.
And for compounds, it's also quite straightforward. You just sum up the molar masses of all the atoms that are in its chemical formula.
Right, add them up.
So, for instance, lithium carbonate, it's used to treat bipolar disorder. Its molar mass is 73.89 grams per mole. Or salicylic acid, you find that in skin treatments, that comes in at 138.12 grams per mole.
This ability, then, to convert between grams, which we can weigh, and moles, the number of particles, that seems incredibly useful, actually fundamental.
Oh, it is.
This isn't just about lab accuracy, is it? It sounds like the bedrock of, say, modern pharmacology, getting that molar mass right. That's the difference between a medicine working, doing nothing, or even being toxic.
Absolutely critical.
Oh.
It's chemistry ensuring safety and efficacy at a really fundamental level. Precision matters.
Okay, so chemistry isn't just about counting and weighing things that sit still. It's fundamentally about change, right? Atoms rearranging, breaking bonds, forming new ones, making totally new substances.
That's the heart of it, yes. That process is a chemical reaction.
And how do we describe these changes?
We use chemical equations. Think of them as concise chemical recipes.
Okay.
On the left side of an arrow, you have the reactants. That's your starting stuff. On the right, you get the products, what you end up with.
Simple enough.
Plus signs separate different substances, and often you'll see little abbreviations in parentheses like S for solid, L for liquid, G for gas, AQ for aqueous, meaning dissolved in water.
Right, I've seen those. And sometimes there's a symbol over the arrow.
Yeah, if you see a delta, like a triangle, over the arrow, that just means heat was needed to get the reaction going.
Got it. Now, this next bit seems really important. Every single chemical equation has to be balanced. Why is that so strict?
It's not just a rule chemists made up, it's a fundamental law of nature. The law of conservation of matter.
Ah, okay. Matter can't be created or destroyed.
Exactly. Atoms can't just appear or disappear or change into completely different types of atoms during a normal chemical reaction.
Yeah.
So you absolutely must have the exact same number of atoms of each element on both sides of that equation arrow. They have to balance out.
So how do you make them balance?
We use whole numbers called coefficients. We place these numbers in front of the chemical formulas. Take the combustion of methane, natural gas, for example. The balanced equation is CH4G plus 2O2G plus 2H2OG. See the 2's.
Yeah, in front of the O2 and the H2O.
Those coefficients ensure we have 1 carbon, 4 hydrogens, and 4 oxygens on both the left and the right. Matter is conserved.
Okay, that makes sense. It's like careful accounting for atoms. And just like stories have genres, you mentioned reactions have categories.
Yeah, it helps to classify them to understand their general patterns. The textbook breaks them down into 5 general types.
Let's run through them.
Okay, first, combination reactions. Pretty straightforward. 2 or more simpler things, elements or compounds, combine to form one single more complex product.
Like magnesium metal burning in air.
Exactly. Magnesium plus oxygen gives you magnesium oxide. 2Mg plus O2, 2MgO. Simple things make one complex thing.
Okay, what's next?
Decomposition reactions. These are basically the opposite. One reactant splits apart or decomposes into 2 or more simpler products.
So breaking down.
Yep. A classic example is heating mercury oxide. It breaks down into liquid mercury and oxygen gas, 2HgO, 2Hg plus O2. One thing becomes multiple simpler things.
Got it. Combination, decomposition. Number 3.
Single replacement reactions. Here, one element essentially kicks out another element from compound. A more reactive element displaces a less reactive one.
Like a swap.
Kind of. Think of zinc metal dropped into hydrochloric acid. The zinc is more reactive than hydrogen, so it replaces it. Zn plus 2HCl8H2, a hydrogen gas, bubbles off, plus ZnCl2.
Okay, single swap. What about double?
That leads us to double replacement reactions.
Yeah.
Here, it's like the positive ions in 2 different reacting compounds just switch partners.
A chemical square dance.
Yeah, that's a good way to think about it. Imagine mixing solutions of barium chloride, BSol2, and sodium sulfate, N₂SO4. The barium and sodium ions swap partners.
So you get?
You form barium sulfate, BaSO4, which is often a solid precipitate, and sodium chloride, NaCl, which stays dissolved. BaCl2 plus now 2SO4, 8 BaSO4s plus 2 NaCl.
Okay. And the last type. Sounds important for energy.
Definitely. Combustion reactions. These are super relevant to our daily lives. They typically involve a carbon-containing compound, usually a fuel, reacting rapidly with oxygen.
Burning stuff.
Pretty much. Burning requires oxygen. The usual products are carbon dioxide, CO2, and water, H2O. And importantly, they release a significant amount of energy as heat and light. Think of your gas stove, a campfire, a car engine, all combustion.
Right. And speaking of combustion, this takes us to something quite serious, doesn't it? The health aspect you mentioned earlier.
It does indeed. Specifically, the issue of incomplete combustion and the really insidious toxicity of carbon monoxide.
Ah, yes. The silent killer. That sounds like something that happens when combustion goes wrong.
Precisely. When fuels like propane, natural gas, wood, even charcoal burn in a place without enough oxygen, like a poorly ventilated room with a space heater
Right.
or a faulty furnace.
Okay.
Instead of producing relatively harmless carbon dioxide, CO2, the reaction doesn't go all the way. It produces the highly dangerous carbon monoxide, CON, instead.
So the equation looks different.
Yeah, for methane, for instance, it might look something like 2CH4G plus 3O2G plus 4H2OG. Notice the CO product instead of CO2, and it uses less oxygen.
But how does this simple molecule, CO, manage to be so devastating? What's its chemical mechanism inside the body?
Well, that's where its danger truly lies. Carbon monoxide is colorless and odorless. You can't see it, you can't smell it.
Terrifying.
It is. So when inhaled, it readily passes into your bloodstream, and here's the crucial part. It binds to hemoglobin,
The protein in red blood cells that carries oxygen.
the very same. Hemoglobin's job is to transport oxygen from your lungs to all your cells. But CO binds to the same site on hemoglobin that oxygen does.
Oh.
And it binds much more strongly than oxygen does. We're talking about 200 to 250 times more strongly.
Wow. So it just elbows oxygen out of the way.
Effectively, yes. It hijacks your oxygen transport system. The CO latches onto hemoglobin and doesn't let go easily, meaning less hemoglobin is available to carry oxygen. Your cells start getting starved of O2.
And the effects.
Even at fairly low levels, say 10% of your hemoglobin is tied up by CO, you can start feeling shortness of breath, mild headaches, maybe drowsiness. Heavy smokers, actually, can hover around 9% regularly.
Really?
Yeah. But if it gets to 30% saturation, symptoms worsen dramatically. Dizziness, mental confusion, severe headaches. And if 50% or more of your hemoglobin gets bound to CO, well, that can rapidly lead to unconsciousness and, tragically, death without immediate oxygen therapy.
That just powerfully illustrates the direct and potentially lethal consequences of understanding these reaction types and, crucially, the conditions under which they occur. It makes you think twice about ventilation, CO detectors.
Absolutely. The chemical specificity of that co-hemoglobin interaction is a really stark reminder of how molecular shape and binding affinity dictate biological effects.
It really is. Now, sticking with crucial chemical mechanisms, you mentioned another incredibly important reaction type, something about electron transfer.
Yes, oxidation-reduction reactions, often just called redox reactions. These are absolutely fundamental and underpin countless processes, especially in biology. They fundamentally involve the transfer of electrons from one substance to another.
Okay, electrons moving around. Is there an easy way to remember which part is which, losing versus gaining?
There is. A very common mnemonic is oil rig.
Oil rig.
Oxidation is loss of electrons. Reduction is gain of electrons.
Oil rig. Okay, I can remember that. Oxidation is loss, reduction is gain.
Exactly.
Yeah.
It's super helpful. When you see like a rusty nail that's iron oxidizing, losing electrons, or the green patina on an old copper roof, that's copper oxidizing.
So in those reactions, one thing loses electrons.
It gets oxidized.
Right. And another thing must gain those electrons.
And it gets reduced. For example, with that green copper, the copper metal, C, loses electrons to become copper ions, C2+. That's the oxidation.
Yeah.
At the same time, oxygen, O2, from the air, gains electrons to become oxide ions, O2. That's the reduction. You can't have one without the other.
Okay. And how does this electron shuffling, this redox chemistry, connect directly to what's happening inside our bodies?
Oh, it's absolutely central, especially to how we get energy.
Yeah.
In our cells, the oxidation of organic molecules, basically, breaking down the food we eat, often involves not just electrons, but the transfer of entire hydrogen atoms, which include an electron.
Right.
For instance, there's a critical molecule, a coenzyme called FAD. Think of it like a little rechargeable battery or shuttle.
Okay.
FAD gets reduced to FADH2 by gaining 2 hydrogen atoms during metabolic processes. Those hydrogens, carrying energy-rich electrons, are then used later in the process of making ATP, the main energy currency of the cell.
So redox is key to energy production.
Absolutely essential. Cellular respiration is a massive series of coordinated redox reactions.
But this raises a question, doesn't it? If oxidation is so vital for energy, can these same processes be harmful if the wrong substance gets oxidized and reduced? What about toxins?
A very important point. Yes, they absolutely can be harmful. Consider methyl alcohol, methanol. It's highly poisonous.
Right. Found in windshield washer fluid, shouldn't drink it?
Definitely not. When ingested, the body metabolizes it through a series of oxidation reactions in the liver. First, methanol, CH4O, is oxidized. It loses hydrogens to become formaldehyde, CH2O.
Formaldehyde? That sounds bad.
It is very toxic, but it doesn't stop there. Formaldehyde is then oxidized further this time, gaining an oxygen to become formic acid, CH2O2.
Also bad.
Also quite toxic.
Oh.
Finally, formic acid gets oxidized to carbon dioxide and water, which are harmless. But the intermediate products, formaldehyde and formic acid, are the real problem.
I see.
They build up and interfere with all sorts of vital cellular reactions, causing damage throughout the body, leading to symptoms like blindness, metabolic acidosis, and potentially death. So yes, while oxidation is crucial for energy from safe fuels like glucose, oxidizing the wrong substance can produce incredibly dangerous intermediates. The specific pathway matters immensely.
That's a powerful example. Okay, so we've covered what reactions are, the different types. But in fields like medicine or manufacturing, just knowing what happens isn't enough. You need to know how much, right?
Precisely. How much reactant do I need? How much product will I get? That's where we need to quantify things.
And how do chemists do that? How do they predict amounts with such accuracy?
That brings us back to those balanced equations and the mole concept. It's all connected. We use mole relationships and mass calculations.
Okay.
Remember the coefficients. Those numbers we put in front to balance the equation.
Yeah, like the 2's in the methane combustion.
Exactly. Those coefficients don't just tell us the ratio of individual atoms or molecules. Crucially, they also tell us the ratio of moles of each reactant and product involved in the reaction.
Ah, so the equation works on the mole level, too.
Yes, this is absolutely critical. It allows us to apply the law of conservation of mass in a practical, quantitative, measurable way using moles.
So if an equation says, for example, 2 moles of silver react with 1 mole of sulfur to make 1 mole of silver sulfide,
Right, 2Ag plus S, Ag2S.
then that 2 to 1 to 1 ratio, that applies to moles.
Precisely. We can use those ratios directly as mole factors or conversion factors. If you know how many moles of silver you start with, you can calculate exactly how many moles of sulfur you need and exactly how many moles of silver sulfide you'll produce.
That seems really powerful for predictions.
It is. And then using molar masses, which connect moles back to grams.
Which we can weigh.
Exactly. We can take it one vital step further. We can calculate from the mass in grams of one substance in the reaction to the mass in grams of any other substance.
So grams of reactant A to grams of product B.
Yep. Start with grams of A, convert to moles of A using its molar mass, use the mole ratio from the balanced equation to find moles of B, then convert moles of B back to grams of B using its molar mass.
Wow. Okay, that's a clear pathway. And hugely important, I imagine, in fields like pharmaceuticals, making sure you synthesize the exact right amount of a drug.
Absolutely essential. Or in industrial chemistry, knowing exactly how much product you'll get from your starting materials. Or, like the textbook mentions, calculating how many grams of oxygen are needed for welding with acetylene. It's quantitative chemistry in action.
Okay, that covers the how much. Now, let's talk about the driving force, the fuel behind these changes. Energy. You mentioned combustion releases energy, but it seems like all reactions involve energy somehow.
They do. Every single chemical reaction involves some kind of energy change.
Yeah.
And for a reaction to even get started, there's an energy hurdle to overcome.
Yeah.
The reactant molecules, they have to collide with each other, first off.
Okay.
But not just any collision works. They need to collide with enough energy and in the right orientation to actually break their existing chemical bonds.
Okay.
This minimum amount of energy required to get the reaction going is called the activation energy. Think of like pushing a rock up a small hill. You need to put in some effort, some energy to get it to the top before it can easily roll down the other side.
Right, the activation hill. And once you get over that hill, some reactions release energy as they proceed and others absorb it.
Exactly. We classify reactions based on their overall energy change. Exothermic reactions are the ones that release heat energy into their surroundings.
Exo, like exit, energy exits.
Perfect way to remember it. In these reactions, the products end up being at a lower energy state, more stable than the reactants were. The excess energy is released, usually as heat.
Like burning fuel.
Burning fuel is a classic exothermic reaction. Or think of the thermite reaction. It produces so much heat, it can literally melt steel to weld railroad tracks. That's extremely exothermic.
Wow. Any gentler examples, maybe health-related?
Absolutely. A common hot pack that you might use for sore muscles works on this principle.
Oh, yeah.
Inside the pack, there's often calcium chloride. When you break the inner pouch, it mixes with water, and the process of it dissolving is highly exothermic. It releases about 82 kilojoules of heat energy for every mole that dissolves.
So the pack gets warm just from dissolving a salt.
Exactly. That heat helps relax muscles, increase blood flow, all from an exothermic process.
That's clever. Okay, so what's the opposite? The ones that absorb heat.
Those are endothermic reactions. Endo meaning into energy goes into the system.
Okay.
In these reactions, they absorb heat energy from their surroundings. This means the products actually end up at a higher energy state than the reactants were. They need that energy input to form.
So they feel cold.
They often do, because they're pulling heat away from whatever they're touching. A fantastic health example is the instant cold pack.
For injuries, right. What's happening inside that?
Usually it contains solid ammonium nitrate in a pouch of water. When you break the inner pouch and mix them, the ammonium nitrate dissolves in the water. But this dissolving process is strongly endothermic.
Ah.
It absorbs about 26 kilojoules of heat from the surroundings for every mole that dissolves. This rapidly drops the temperature of the pack down to maybe 4 or 5 degrees Celsius.
Perfect for reducing swelling.
Precisely. It pulls heat away from the injury, constricting blood vessels and reducing inflammation. All thanks to an endothermic process.
It's really fascinating how these fundamental energy concepts translate directly into simple, common medical treatments we use all the time.
Isn't it, though?
Yeah.
Chemistry is everywhere.
So besides the energy, what else controls how fast these reactions actually happen? Some seem instant, others take ages, like rusting.
That's a great question. The rate of a reaction, basically its speed, is critically important, especially in living systems where timing is everything. It's primarily influenced by 3 main factors.
Okay, what are they?
First, temperature. Generally speaking, increasing the temperature makes reactions go faster.
Hotter means faster. Why is that?
Because at higher temperatures, molecules have more kinetic energy. They move around faster, collide more often, and crucially, more of those collisions will have enough energy to overcome that activation energy barrier we talked about.
Makes sense. More energetic collisions.
Exactly. That's why we refrigerate food, right? To slow down the chemical reactions that cause spoilage, low temperature, slow reaction rate.
Ah, okay. And in the body.
Same principle. A slight fever actually increases your metabolic rate, reactions speed up. But conversely, during some complex surgeries, like certain heart operations, doctors might deliberately cool the patient's body down significantly, maybe to 28 Celsius.
Why would they do that?
To slow down the body's overall metabolism, reduce the brain's demand for oxygen during a period when blood flow might be temporarily interrupted. Slowing reactions protects tissues.
Wow. So temperature is a powerful control knob for a reaction speed. What's the second factor?
But concentration of reactants. Basically how crowded the reactants are.
More stuff means faster reaction.
Generally, yes. If you have more reactant molecules packed into a given volume, they're simply going to collide more frequently. More collisions mean more chances for a successful reaction-causing collision to happen.
Okay. Any health examples?
Sure. If a patient is having trouble breathing, perhaps due to lung disease, they might be given supplemental oxygen or even a breathing mixture with a higher percentage of oxygen than normal air.
Right.
What that does is increase the concentration of oxygen molecules in their lungs. This speeds up the rate at which oxygen binds to hemoglobin in their blood, helping them get the oxygen they need more efficiently.
So higher concentration drives the reaction faster. Makes sense. Temperature, concentration. What's the third factor?
The third one is incredibly important, especially in biology. Catalysts.
Catalysts. I've heard that term. They speed things up, right? But how?
They do speed things up, often dramatically, but they do it in a very specific way. A catalyst provides an alternative pathway for the reaction to occur, a pathway that has a lower activation energy.
Ah, so they don't just make molecules move faster like heat does. They actually lower the energy hill.
Exactly. It's like finding a tunnel through that activation energy mountain instead of having to climb all the way over the top.
Well,
this allows the reaction to proceed much more quickly at a given temperature.
Mm-hmm.
And importantly, the catalyst itself isn't used up in the reaction. It can facilitate the reaction over and over again.
Are they common?
Hugely common in industry making plastics, fuels, fertilizers. But perhaps their most vital role is inside us. Our bodies rely on biological catalysts called enzymes.
Enzymes, right. Proteins mostly.
Mostly proteins, yes. Enzymes are incredibly specific and efficient catalysts. They make virtually all the essential chemical reactions in our metabolism happen at the rates needed to sustain life. Without enzymes, most reactions in our bodies would be far, far too slow at normal body temperature. We simply couldn't function.
So catalysts, especially enzymes, are basically essential for life's chemistry to happen on life's timescale.
Couldn't have said it better myself. They are absolutely fundamental.
Wow. Okay, we have covered a lot today. From, the challenge of counting invisibly small atoms with the mole, to balancing the books with chemical equations, understanding the different reaction types like combustion and redox.
And their health implications, like with CO poisoning or metabolism.
And then quantifying reactions using mole ratios and molar mass, understanding the energy changes, exothermic, endothermic, hot packs, cold packs.
Activation energy.
Activation energy. And finally, what makes reactions speed up or slow down? Temperature, concentration, and those crucial catalysts, the enzymes.
It really forms the foundational language of chemistry, doesn't it?
Yeah.
And it's absolutely essential for anyone going into health or life sciences.
Yeah.
Understanding moles, balanced equations, reaction types, energy. It helps you grasp everything from how drugs work to how our bodies function to environmental issues. It's the underlying machinery.
So the next time you hear about, say, blood oxygen levels or a specific drug dosage or even just how your body gets energy from food, you'll have a better sense of the fundamental chemistry that's really pulling the strings behind the scenes.
Exactly. It's a powerful foundation,
Right.
even if it seems invisible sometimes.
It really is. We hope this deep dive has given you maybe a fresh perspective and definitely some valuable insights into this world of chemical quantities and reactions.
Certainly hope so. It's fascinating stuff once you start connecting the dots.
Thank you so much for joining us on this deep dive. Last Minute Lecture Team. A warm thank you from the Last Minute Lecture Team.